Good morning to all of you. In previous session, we have seen pole zero cancellations, where we have seen we can cancel the common pole and zero from the system function, or when we are multiplying system function with the z transform of input signal. So by using that pole zero cancellation, we can identify the impulse response of the system as well as response of the system, that is small h of n, or the response of system denoted as y of n. Today we'll be discussing the Schur-Cohn stability test. So the Schur-Cohn stability test. So the stability of a system is determined by the position of the poles. We know that if the poles lies outside the unit circle, then system is unstable, right? So the poles of the system are nothing but the roots of the denominator polynomial of system function. Just for example, if we are indicating system function h of z is equals to the system function, if we are indicating as the combination of numerator and denominator, in numerator it contains the polynomial b of z, and in denominator if it is containing the polynomial a of z, right? So for identifying whether the given system is stable or unstable, we'll be identifying the poles of this system. So the poles of the system is nothing but the roots of this denominator polynomial a of z, right? So for example, a of z is the what you can say mth order polynomial, right? So it can be indicated as, just for example, a of z is equals to 1 plus a1 z inverse plus a2 z to the power minus 2, right? Plus and so on, plus am z to the power minus m. Okay, so it is the mth degree polynomial or mth order polynomial. So it will have m roots, so those will be nothing but the m poles of this system. Okay, so there are several computational procedures that can be used in determining if any of the roots of this a of z lie outside the unit circle, right? So if any one of roots of this a of z lies outside the unit circle, then system is unstable, right? So those roots are nothing but the poles of this system. So if any one of the roots is lying outside the unit circle, that means the pole lies outside the unit circle, then we can say that system is unstable. So these procedures which are used, these computational procedures which are used to identify whether the roots of this polynomial lies outside the unit circle are called as the stability criteria. Okay, so this Schur-Cohn stability test is one of the stability criteria, okay, to check the stability of given system, right? So these are also called as what? Stability criteria for identifying the stability of given system, right? So in case of the Schur-Cohn stability test, for the stability of given system, we are using this system function which is characterized by h of z is equals to b of z upon a of z, where this a of z is the denominator, b of z is the numerator, and we'll be identifying these denominator polynomial roots, which will be referred as the poles of the system, right? So this denominator polynomial can be in simplified form or in compact form can be represented as am of z is equals to, you can indicate it as uh, summation k is equals to 0 to n am of k, right, into z to the power minus k. Okay, or you can simply indicate it as am into z to the power minus k, right? Or ak z to the power minus k. So here the value of this k is varying from 0 to m, right? So here initially you will have a0, that is nothing but a0 into z to the power 0, so it will be 1. But for that purpose this am of 0 should be 1. Okay, this am of 0 should be 1, then and then only the first term will be 1, and the next will be k value will be 1, so it will be a1 am of 1 into z inverse, then am of 2 z to the power minus 2, and so on, right? So likewise, so in more compact form we can indicate this mth order polynomial. So this m indicates the polynomial of degree m, right? So or m indicates the degree of polynomial. Okay, so this particular equation is the polynomial of degree small m, right? So this is nothing but the denominator of the given system function, right? So whatever denominator is there, in that denominator the first term should be 1 and the remaining term should be the coefficient terms of z in such a way that z inverse, then z to the power minus 2 up to z to the power minus n, depending on how many terms are there in the denominator. So the reciprocal or reverse polynomial of this am of z is denoted as bm of z, right? So from this am of z we'll be identifying the reciprocal or reverse polynomial, which is indicated as bm of z. So this bm of z will be identified by using am of z, right? So this bm of z as the equation, simply I'll write here only. So bm of z will be equals to, so this am of z will be multiplied by z to the power minus n, and this am of z will be simply taken in reverse order. Okay, so am of z inverse will be there. So from am of z we can identify am of z inverse, and then am of z inverse will be multiplied with z to the power minus n. Okay, so this is how we'll be identifying the reciprocal or reverse polynomial bm of z from am of z, right? So the coefficients of bm of z are the same as those of am of z, right? But it will be in reverse order, right? So it will be reverse order polynomial. Okay, so in the Schur-Cohn stability test, to determine if the polynomial a of z has all roots inside the unit circle, we compute the set of coefficients. So those set of coefficients are called as reflection coefficients. So these set of coefficients are called as reflection coefficients, right? So those reflection coefficients are simply indicated as k1, k2 up to, just for example, kn, depending on the order of polynomial. So these reflection coefficients are identified from the polynomial am of z, that is nothing but the denominator polynomial am of z, right? So initially we will take this denominator polynomial as am of z. From am of z we will identify the reciprocal or reverse polynomial bm of z, right? This reflection coefficient k1, k2 up to kn will be identified from this denominator polynomial am of z, right? And then we compute the lower degree polynomials from am of z. Okay, so uh, the, those lower degree polynomial depends on the degree of polynomial that is am of z. So from am of z, we'll identify the lower degree polynomial am minus 1 of z. Okay. So for computing these lower degree polynomials, we have this equation, that is am minus 1 of z is equals to am of z minus km. So this km is nothing but the reflection coefficient. Bm of z, Bm of z is the reverse order polynomial which is identified from the denominator polynomial am of z, right? Whole upon 1 minus again reflection coefficient square, that is km square, right? So this km is nothing but this is identified from the am of z simply, right? So the Schur-Cohn stability test states that the polynomials a of z has all its roots inside the unit circle if and only if the coefficient km, okay, that is the uh, km is the coefficient which is identified from the denominator polynomial am of z. Okay, so this reflection coefficient km satisfies the condition, that is mod km should be less than 1. Okay, so if it is this reflection coefficient mod km is less than 1 for all m, because we'll be initially identifying it for m, then m minus 1, then m minus 2, and so on. Okay, so if it this mod km is less than 1 for all m, that is m is 1, 2 up to n, then we can say that the system is stable, right? So that is if km or km is less than 1, system is stable. Okay, so we'll be provided with the system function. If system function is not given, only input output function is given, that is y of n is given, then you can take the z transform of that y of n. Then after taking z transform of y of n, we can identify y of z upon x of z, which is nothing but the h of z. Then from that h of z, we will take the denominator polynomial. So denominator polynomial should have this form, right? That is 1 plus the coefficient multiplied by z inverse plus coefficient multiplied by z to the power minus 2, and so on. So this denominator polynomial will be considered as am of z. So from this am of z, you can identify the value of km, right? That is the reflection coefficient km, as well as from am of z, you can identify the reverse order polynomial or reciprocal polynomial bm of z, right? So after identifying bm of z, you can identify the lower order polynomial. You have to identify lower order polynomial till you doesn't get the a1 of z. Okay, so basically this am minus 1 of z will be utilized for identifying the lower degree polynomial. So for identifying this lower degree polynomial, we are using am of z, that is the denominator polynomial, minus reflection coefficient, which is determined from the am of z. Then the reverse order polynomial, that is bm of z, it is again determined by using the am of z, that is denominator polynomial, divided by 1 minus reflection coefficient square. And if this reflection coefficient mod is less than 1 for all values of m, then we can say the system is stable. Okay, so to summarize, we have these equations. Okay, first we have h of z. H of z is as b of z upon a of z, right? And the a of z is nothing but am of z, and it has form summation k is equals to 0 to n am of k z to the power minus k, where am of 0 is equals to 1. From am of z, we'll be identifying km, and this mod km should be less than 1. Then after that, from am of z, we can identify bm of z. The equation for bm of z will be equals to z to the power minus m. So we are multiplying z to the power minus m and am of z inverse, right? So after identifying bm of z, we can identify the lower order polynomial, that is am minus 1 of z. So the formula for that am minus 1 of z is am of z, okay, am of z minus km bm of z whole upon 1 minus km square, right? So you will get a1 am minus 1 of z, okay. So again, from am minus 1 of z you will get the coefficient km minus 1, right? So if mod km minus 1 is less than 1, then you will identify b2 of bn minus 1 of z, right? So again, from bn minus 1 of z and am minus 1 of z, you can identify am minus 2 of z. So this is recursive process, right? So it will be continued till all the coefficients are not identified, because you will be identified it for m is equals to 1 comma 2 and so on up to maybe n, if depending on the degree of polynomial, if it is nth order polynomial, right? So this procedure will be repeated, right? So this process will be utilized for identifying whether the system is stable or unstable, correct? So these are the formulas which are used in the Schur-Cohn stability test. Okay, let's try to solve one example here. So here the system function is given h of z, right? So it is in the required form already, right? And we have to determine the whether the given system is stable or unstable, right? So here the given system function h of z is equals to what has been given, 1 upon 1 minus 7 by 4 z inverse minus 1 by 2 z to the power minus 2. Okay, so uh, the reflection coefficient here is basically, before writing the reflection coefficient, we will write down the denominator polynomial as am of z. Okay, so as the denominator polynomial has the degree 2, okay, it is the second order polynomial. So therefore instead of writing am of z, we'll write it as a2 of z, okay, so because it is the second order polynomial. So a2 of z from this am of z, which is identified from the h of z, is 1 minus 7 by 4 z inverse minus 1 by 2 z to the power minus 2. Okay, so here we begin with what, a2 of z. Okay, so it is the second order polynomial. Okay, so therefore the reflection coefficient k2 from k2 of z is, so the value of k2 is equals to minus 1 by 2, right? Because these are nothing but the coefficients. So here the first coefficient is 1, second one is minus 7 by 4, and third one is minus 1 by 2. So first reflection coefficient is minus 1 by 2. So we'll verify whether this mod k2 is less than 1 or not. Okay, as mod k2, because if you are taking mod of this minus 1 by 2, so it will be simply 1 by 2, so it will be 0 0.5, and 0 0.5 is less than 1. Okay, so as mod k2 is less than 1, we proceed to identify lower degree polynomial. Okay, identify the lower degree polynomial. Okay, so lower degree polynomial will be a1 of z. Okay, so that is nothing but am minus 1 of z. But to get this a1 of z, we should know the reverse order polynomial, that is bm of z. Okay, so I'll rewrite this a2 of z here. So a2 of z is equals to, what is that, 1 minus 1 minus 7 by 4 z inverse minus 1 by 2 z to the power minus 2. Okay, so it is nothing but the a2 of z. So from the a2 of z we will initially identify the reverse order polynomial or the reciprocal polynomial. Okay, so the reverse order polynomial b2 of z is, so what will be the formula for b2 of z? So the formula for this bm of z was z to the power minus m. Okay, that we are written here, z to the power minus m am of z inverse. Okay, so it will be as in place of m the value is 2, so it will be z to the power minus 2 a2 of z inverse. Okay, so if I'm writing a2 of z inverse, so wherever there is z, so that will be replaced with z inverse, right? So simply it will be z to the power minus 2, right, multiplied by, if I am replacing z with z inverse in this a2 of z, so it will be 1 minus 7 by 4 z minus 1 by 2 z square, right? And if I'm multiplying it with z to the power minus 2 inside this bracket, so I will get this bm of z, that is nothing but b2 of z. Okay, so it will be simply z to the power minus 2, right, minus 7 by 4 z inverse, right, and minus 1 by 2. Okay, so that will be b2 of z, which is the reverse order polynomial identified from the a2 of z. Okay, now the lower order polynomial a1 of z. Okay, so this a1 of z, that is am minus 1 of z, will be identified from a2 of z minus k2 b2 of z whole upon, because the formula is am of z minus km bm of z upon 1 minus km square. Okay, that is k2 square will be there, right? So that will be the formula. Okay, so we have to substitute these values here. We have a2 of z, right? We have a2 of z, the value of k2 is minus 1 by 2. Okay, so the value of k2 is minus 1 by 2, right? And b2 of z were here, were identified here, right? So by substituting all these values, we'll get a1 of z. Okay, so the a1 of z will be equals to, the value of a2 of z is 1 minus 7 by 4 z inverse, so it is 1 minus 7 by 4 z inverse minus 1 by 2 minus 1 by 2 z to the power minus 2. Okay, minus, so here we are to substitute the value of k2. K2 is minus 1 by 2, so minus minus plus will be there, so plus 1 by 2 I can write here. Okay, and then multiplied by b2 of z. B2 of z is z raised to power minus 2 minus 7 by 4 z inverse minus 1 by 2. Okay, so z to the power minus 2 minus 7 by 4 z inverse, then minus 1 by 2. Okay, and whole upon, in here 1 minus k2 square, so k2 is minus 1 by 2, so minus 1 by 2 square will be plus 1 by 4, right? So it will be 1 minus 1 by 4 will be there, right? So if you simplify this polynomial, right, so after simplification, so here you will get a1 of z is equals to, you just multiply the bracket with 1 by 2, right? So here you can see that 1 by 2 z inverse z to the power minus 2, it is minus 1 by 2 z to the power minus 2 and plus 1 by 2 z to the power minus 2, so it will be 0, right? So this will be 0. Similarly you can find it there, this plus 1 by 2 minus 1 by 2 will get multiplied, right? If you multiply this constant, that is 1 minus 1 by 4, so it will be simply 3 by 4. If you send it in the numerator, so it will be 4 by 3, right? So if you simplify it, so you will get simply the value a1 of z is equals to 1 minus 7 by 2 z to the power minus 1. Okay, so this is a1 of z. Okay, it is a lower order polynomial after simplification, right? So from a1 of z you will get the reflection coefficient k1. Okay, so the reflection coefficient k1 is simply k1 is equals to minus 7 by 2, right? So if you identify the relationship of this k1 with this mod k1 less than 1, okay, so if I'm taking the modulus of this 7 by 2, okay, minus 7 by 2, so it will be 7 by 2. So mod k1 is not less than basically 1. Okay, so mod k1 is greater than 1. So since here mod k1 is greater than 1, it follows that the system is unstable. Okay, so there is no need to identify the basically here we already identified the a1 of z. Okay, so we identified the reflection coefficient k1 because as we have seen in previous slides that this reflection coefficient will be identified for various values of m, 1, 2 and so on, right, starting with this last value of m. Okay, then previous likewise we will be identifying all these coefficients. So here we have already identified the k1 coefficient, but as this k1 coefficient is mod k1 is greater than 1, so therefore system is unstable here. Okay, so this is how you are applying Schur-Cohn stability criteria where for identifying whether the given system is stable or unstable. Okay, so initially we had taken the system function, considered its denominator polynomial as a2 of z. From that we identified the reflection coefficient k2. Mod k2 is less than 1, therefore we have identified the next coefficient, that is k1. If this k2 mod k2 is greater than 1, then here itself we have stated that we might have stated that the system is unstable, but as this k2 mod k2 is less than 1, therefore we have identified b2 of z as well as the a1 of z, that is lower order polynomial from a2 of z we identified by utilizing a2 of z, b2 of z and k2. Okay, so after identifying this a1 of z we identified the reflection coefficient k1. Okay, as this k1 mod k1 is less than 1 is not less than 1, right? So mod k1 is greater than 1, therefore we have concluded that system is unstable. If this mod k1 was less than 1, then we can say that the system is stable. Okay, so this is how we will be applying Schur-Cohn stability criteria for checking the stability of given system. This process you can also implement by writing some code in C language, or maybe in Java, maybe in Python, or maybe in MATLAB or Scilab, right? So this Schur-Cohn stability criteria can be implemented by using software program, right? So you can just try it by implementing in any programming platform. Okay, so in next session we'll see the Fourier transform. Okay, so we'll be discussing Fourier transform in next session, right? So thank you for joining this session.